My plan was to go through um, the lectures and sort of try to extract the main points. So I typically I have for every lecture I have here in blue the number. The number is really what the files look like when you download them. The PDF files have a number, and that's roughly the number. I think it's exactly the number of the lectures, maybe except of the one I started, maybe it's zero. I don't remember, but something like that. So one, for instance, is the introductory lecture. That was the first lecture, and that's how you can orient and look up the other slides and so on. So the first introduction, I just talked about what this is about, what autonomous robotics is about, and I'm reminding you of this notion that robots are programmable devices in general. That makes them flexible, right? That was the classical view that rather than have particular special machines, you have programmable machines that are already more flexible. That's classical industry robots. And then the notion of autonomous robots would be robots that program themselves. That was the original notion, the artificial intelligence notion, self-programming machines. And then more concretely really means that they generate their programs or their behaviors based on their own sensory information about the world, typically by sensors that are on board. There's some exceptions to that. And that's an important notion to even understand, right? And that's a big difference between autonomous and classical robots. Classical robots, the programmer, the human programmer, knows everything about the world that is needed to know. And therefore, they only work in environments where that information is vertical because, the programmer had the correct database about the correct objects on the conveyor belt and all that. The autonomous robots have their own sensors to find out about the world. And I then said, it's still robots. Here's again the sound. It's still a robot that has tasks. So it's not that these robots just do anything. It's robots that are given tasks by a human user or programmer, and then the notion would be that task is given at a high level, in the ideal case, even by human intuitive interaction, like a human using gesture and language, like Yanis Yosifidis does. And then so then it doesn't need to give the robot a detailed description of the world. The robot can find out about the world and then actually has to establish a link between what the user instructs and the world by knowing what object the user is talking about. And that's what where the robot might be using things like a gesture. I think here, Yanis is pointing at an object. Here, for instance, pointing at an object, and the robot knows which of the two screwdrivers is supposed to be picked up right now, right? So that's was a very common scenario of thinking of autonomy in this sense. It's some kind of limited autonomy, right? If you think of a animal, that's of course autonomous. An animal will decide to feed or to hunt or to pursue, you know, sexual partners uh, under its own policy, right? And that's not what we are actually looking at with robots. We're looking at robots that get tasks from the outside. And that's actually a very common thing, of course, for humans to do as well. When we're working and acting in groups, we have goals and tasks. So it is still in the spirit of capturing human-like behavior because we're not actually just freely. It's just one level where we're really freely roaming, but in many contexts we have tasks, right? And then I argued that it's an interesting field. I mean, this original motivation to have such robots has some justifications for certain application cases, but we would say currently that it's largely also just a playground of research. And one aspect of it is very interdisciplinary. That is, to achieve that, you have to have a lot of things in place, and I list again some of those things here. And that's an interesting challenge. It's an interesting challenge for teaching, for technology, developing principled approaches to that. And one aspect of that is to have these architectures. I mentioned the Sense Plan Act architecture that were at the origin of thinking about artificial intelligence. Some of those ideas are still around. So the original notion still persists, was that you have modules that deal with particular parts of this task. Here, the crudest level, just talking about sense, model, plan, and act. And they would contain their information, and it would be well defined what kind of information they give out, and it would have a centralized world representation in the model, and would have a preferred level where all the artificial intelligence takes place. That's when the system plans. And you see that the planning here would then be based on knowing the world through the model, just like the classical programmable robot, with the exception that this model was supposed to be autonomously acquired. And then this planning, of course, also has to be automatic, right? It's not a programmer that designs that. It's automatic planning. And classical symbolic approaches to autonomous planning actually develop algorithms that can do that. Given a world model, they can make plans like that. This whole field that I didn't really touch much. Contrasted that with the behavior-based architectures in which the individual sense, plan, act things have trivial planning. That is, they sense, it's plotted horizontally here, that their own sensors, they have a very simple rule how to act on sensor information that is directly translated into action. And then you might have multiple different ones. You call each one a behavior, multiple different ones. And there is the only architecture-like thing is that these might be interacting, like one might suppress the other one, there might be selection, which of those is active, and there might be sometimes be something where one of those gives its output to the other as an input, and you can just chain them, or one subsumes another is a way to talk about that. And this is an influential idea that is being used a lot, and typically they are combined. That is, the state of the art is that a lot of the machines have these kind of behavior-based controllers here. It's called schema-based at a low level. This really does the detailed action on the current sensor information. But they might also have a more classical sense plan act architecture on top that does classical programming and planning, which again wasn't covered so much in my lecture, to then modulate this low-level stuff. And without that low-level stuff, we really can't achieve much in the real world. But only the low-level stuff has made it harder to achieve more complex and strategic tasks, which is still a problem, by the way. Still not so much that is achieved with these higher-level behaviors. The very successful cases in the military have a lot of direct user interaction here at this top level. So they have limited autonomy. Oh, I'm again using my cursor on the wrong screen. I just noticed. Sorry. Yeah. Sorry. Okay. So that was just some highlights from the introduction, and I mentioned those that are easy to ask questions about. So, of course, I assume that you know what autonomy means when we have a whole lecture course about autonomous, right? Yeah, then we had this module that number 2, which was this dynamical systems approach. We did not have a separate dynamical systems tutorial, but I was going to use this core element that you do a lot of exercises on, also to review ideas in dynamics, and hope that you will be able to ask questions about dynamical systems as well. So in a nutshell, these are the 4 concepts that we have. Behavioral variables, I'll say more about that in a moment. The time courses for them are generated from dynamical systems in the form of attractors, which the system tracks. That is, the attractors change as sensory information changes, and therefore they move with the attractors, and then bifurcations are used to make decisions to become flexible. And very concretely, this had the 2 components that we already discussed in this simple example. There's a much more general approach that I only gave you the most elementary examples for. These examples, obstacle avoidance and target acquisition, where the variables are heading directions, or some arbitrary world axis from which you have your heading direction. This angle here, that will be the heading of the vehicle. So it's in an external reference frame, but the reference frame is arbitrary. You don't actually need to estimate it. And then all the other information, like the information about directions to a target and directions to an obstacle, are in that same reference frame. So you could say they constrain the variable. So you could say the target is a desired value or prescribed value for the behavioral variable, like a set point in control theory, while the obstacle angle is a undesirable value that was then modeled as a repeller. And it could be a whole range of values because you want to avoid any range where you hit the obstacle. So that's the use of this behavioral variable, that the constraints can be expressed as values or ranges of values of these variables. And you already see here for this concrete case, and I'll anticipate something we'll discuss later, that these variables are velocity type variables, right? They are directions in the world. The directions in the world are directions which you can move. It will be the directional aspect of the velocity of the robot, right? If the robot then moves forward along that direction, then you actually have the velocity vector. And therefore, when we're saying attraction to the target, we're talking about the attraction to that velocity that puts you the vector, the velocity heading direction that takes you to the target, or the repulsion from the obstacle. And that really means here from the direction that leads to the obstacle, from the velocity, right, that would take you to velocity, that would take you to the obstacle. While later we'll look at the potential field approach, which repels or attracts you from the position of the target or the obstacle. That makes a big difference. Good. So we formulate then dynamic systems about these behavioral variables. And many of you, of course, know dynamical systems as differential equations. We are using the qualitative theory of dynamic systems, that is looking at fixed points, attractors, repellers, bifurcations, so on, so characterizing the whole flow of the dynamical systems. And I might ask a few questions about dynamical systems just per se, because that's an important goal of the course, to have an intuitive understanding of this sort of theory. So fundamentally, dynamical systems are systems in which you have a limited set of initial conditions that you need to predict the future, to predict their future values. The set of values you need is called the state space. Here, heading direction would be assumed to be sufficient to know the initial heading. Here's some arbitrary variable x. It could be a whole vector that you need. And then the dynamical system predicts the future intuitively if the rate of change of that variable is a function of the variable or the whole vector, the red line here. Then if you know anywhere your initial position, you know your instantaneous rate of change. And from that, you can predict the infinitesimal next step in time, next time step inner state, and can iterate that. That will be the numerical way to do it. It's also sort of a conceptual way to think about it. And thus you can talk about the evolution of the future. So it's about time courses, but it's not just, time courses per se. It's time courses that are predictable in that way. You could say that you can compress the information in that system to just a state space. And then from that, you can predict time courses through a law. This is the law of motion here, the dynamical system, right? This red line. Complication in the approaches that we'll be looking at is that this red line, the law, also changes as you move around. But that is, is caused by, the function f here depending on something else, namely on the vehicle moving around in the environment. And we're at every moment in time, we're assuming that the function f is given, is fixed. And we have to make sure that the change of this equation that depends on sensory information is slow enough so that the dynamic system still determines what happens on a relevant timescale, the timescale of the dynamics of this evolution here. And that's how the system can track the attractors. When the dynamics changes too quickly, the attractor might be moving all over the place, and the solutions that we'll observe will no longer be toward the attractor, because by the time the system has started to change its state, the attractor has already moved somewhere else. So we're always looking at that limit case where the change of the dynamic system, the red line, is slow compared to the time courses that the dynamics itself generates. And this can be made exact by looking at the eigenvalues, the time scale in the mathematical sense. So attractors fixed points are already anticipated. So a fixed point is just a constant solution. So mathematically, the zero crossings of the dynamical law. So if it's a vector, it's this whole equation being zero, and that's the solution. Because if it's a zero of the function f, then the rate of change being f at that point is correct. The rate of change is zero. It's a constant solution. Fixed points can be stable, unstable, can be marginally stable. The stable ones are the ones that attract the neighboring solutions. So this whole set an environment in one dimension for one variable is just an interval. in multiple dimensions might be a little ball, and every initial condition inside that environment is converging in time as time increases, converges to that fixed point. That's called a fixed point attractor. And that's what we're dealing with as the states that are going to generate behavior, control behavior. This is what control theory does for the physical control of the robot, is make sure that around the set points are attractors. This is ensured by the real part of the eigenvalues having negative value. And we're using this for these behavioral variables, and therefore we're using this to make this a method of planning. Well, that's really, if I should say, into all terms of planning. And so when you have a system like that with an attractor, if now the red line deforms, moves around as sensor information changes, it's this very attractor property that makes that the state space will track the attractor. So if it shifts, it will also shift and follow the attractor, right? That's the central trick. So we're always sitting in the attractor, but we might be doing interesting things because the attractor moves around as the dynamics changes. It's a little complicated, right? And then the bifurcations are instabilities. So there are points where a fixed point disappears or appears out of nowhere due to loss of stability or acquiring stability here. So this is the pitchfork bifurcation, which we often use, where there is a fixed point with a negative slope here that predicts stability, and there's one with a positive slope that's unstable. This is the positive one, the negative one, and we have a parameter here in the normal form, alpha, where you can shift the curve up and down, and when you shift the curve down, these two collide here. They're now, the slope is flat. They are at this point here, and they're now half stable in a way. So from still attracted here from the right, but then going off to minus infinity on the left. And beyond that, there is no more fixed point. So this is gone, right? This will be, if you go from a positive alpha to negative alpha, that will be a case where a stable state is lost. And the system would then go here off into minus infinity, and it would only do something meaningful if there is another attractor somewhere further on the left axis, which is what in practice is arranged in our systems. For heading directions, a periodic space, you have a chance to go explore the whole state space and find another attractor. And so that's how you can qualitatively change the dynamics, make a decision. And I'll illustrate that again in a moment. So these are the abstract mathematical concepts, and concretely we did it then for heading direction. Again, this is the definition, and this is how we implement in a dynamical system the attractor behavior, the target acquisition behavior, make an attractor at the direction toward the target, and then the system will move to the attractor. So for instance, if you're in this initial condition, this will make that your heading is turning toward the heading to the target. That takes a certain amount of time before you've actually reached that correct direction to the target. This needs a tar here. This psi is supposed to be psi tar, that same psi here. And if this other variable that we didn't really discuss much, but in the literature you looked at, of course, there's also dynamics for the forward speed, how fast the robot is moving. And depending on that speed, of course, it may take some time and thus also some distance for the robot to actually turn. Like, for instance, if you're in this position, the robot might have moved forward a little bit before it has already turned its direction. And that will mean that the angle under which the target is seen has slightly shifted, right? And that will mean that this red line has shifted as the robot relaxes to the attractor. But that doesn't matter because it will continue to go to the now slightly shifted attractor, and it will end up in a correct configuration where it's pointing exactly along the line of the target, and these two will be the same. But it will be not the same target direction as initially because of that fact that as you move around the world, the angle to the target changes. If the target is very far away, it's the moon, then you can neglect that, and it will be purely just changing direction to head to the target. But if the target is relatively close, as you're converging to the direction of the target, you are moving in space enough for the direction, the bearing of the target to change a little bit, right? Just to repeat that point. That's a core idea of this approach here. And then for obstacles, you have just essentially it's like target acquisition with time running backwards. That is where there was a negative slope before, now you have a positive slope, repeller, and that makes that if you're a little bit to the right of it and heading, you're moving off to the right. If you're left to the left, you move around the left, and so it's a decision point, right? Your initial heading relative to the target decides if you go around the target on the left or on the right. And you can see it's a very concrete case of a decision making that comes from an unstable fixed point. That's how the instabilities force decisions as well. These curves are parameterized by three things, namely where the zero crossing is, which is the meaningful thing, right? That refers to the target or the obstacle. The steepness of that, that is the strength, how strongly it weighs, how strongly it influences the change of heading. That is what has to be just right for the system to be able to track, but not to be too fast. It also, I mentioned, it has to do with whether you can actually numerically on the computer of the robot really solve this equation fast enough. And then the range, that is over which range are you attracted or repelled. For targets, we typically want to attract over the whole range, and the heading direction happens to be a periodic variable. So that just means that we make sure that there's only one other fixed point at the opposite end where you decide. While for target acquisition, for obstacle avoidance, we just take a range up until we're no longer in conflict with the obstacle, and it's sideways enough for us to no longer be interfered with. And if you were to make that broader, it would interfere with moving in just about any direction. We've generalized this approach to other problems where it's not angular variables, and one can use similar logic for that. So I showed this one case, and I'm taking the case that's more realistic, where we're going really for obstacle avoidance through a bifurcation. And this would be the case where there are two obstacle contributions here in orange that are not in conflict with the target and not with each other. So one erects a repeller here, the other is with this one here, repeller there, and the attractor in the middle comes from the target contribution here in this color. In the green is the attractors, and red is the repellers. And you see that the repellers are exactly where the individual contributions would want to put them, and the attractor is where the individual target contribution would put it. So inside here you have the same that you would have for each individual contribution. And outside you get some kind of extra attractors for going around the whole configuration. They would usually, for the repeller term, they would be just sort of the semi-attractor at the end of the repulsion, right? And here the semi-attractor at the end of the repulsion. And here, because of the target term, they are made into real attractors because the target would push toward the center, and then this one is pushed below, and that makes that now you have a real, the black line is the sum of these, you have a real attractor here. So you have three attractors going around the center, around the left, or around the right obstacle. And then when we bring these constraints into conflict, we can arrange for the right bifurcation to happen, which wipes out the attractor in the center, replaces it by a single repeller, because now the two repulsive forces overlap so strongly that their sum, this black line, has a single fixed point with a positive slope. And the vote here of the target, which has a smaller slope, is weaker, is overruled. And then what you have remaining are the other two attractors around that. And that would be a typical bifurcation where the two repellers collide with the attractor, annihilate the attractor, and go away. This is the pitchfork, which only is true if everything is exactly symmetrical. And then you would be switching to one of the two other attractors that are still available. And this would be a case there's always an attractor available along the full circle. And so this is the argument I just made previously, that you're always sitting in the attractor, you're tracking the attractor as it moves around. Yeah, so we actually even looked at this as a model of human behavior. There's this work by Fajan, which studied that is put people into different situations where they suddenly see a target, suddenly see an obstacle, and looked at the turning rate as a function of the current heading. The heading was here centered in the heading toward the target, and you see essentially this attractive forcelet, the negative slope going through the target angle. You see that when the target suddenly appears out of nowhere, there's this initial transient that is not consistent with the equation that we had. We would say at any of these headings, we should have the same initial turning rate, and that required this second order turn to be headed in some kind of, takes a little amount of time to get onto this correct dynamic curve, and you analyze that in exercise. This is the same plot for different initial distances from the target, and you see that the second order model just gets that just right. And then they also looked at obstacle avoidance. So the obstacle is here at the origin, and there see you have the positive slope, the repulsion force that then decays off. And it's a function also of the initial angle and the initial distance from the obstacle in a way that can be modeled here. And you had a whole exercise where you saw that there's like a second order term. So if you neglect the second order term, you say the inertia is zero. Then you see you put this to the left-hand side, and then you have phi dot equals all these terms, and that will be the attractor dynamics we just discussed. And so it's some sort of flow path filtering on that, where turning away takes a little bit more time because you have inertia, let's say. That will be a possible explanation. I'm not expecting you to understand the mathematics of this now or know this by heart. Maybe just to remind yourself that it is this model is, with this complication, is actually a model of human locomotion. It's also of animal locomotion, by the way, which wasn't really studied in the course, which is interesting, right? This is a very simple phenomenological model and describes quantitatively the behavior of humans locomoting away from obstacles toward targets. Yeah, so that's the second lecture, and that contains a lot of the stuff that the core was aimed to teach you, this way of dynamical systems being used for planning, attractors, repellers, qualitative dynamics, instabilities, and maybe also this interdisciplinarity, that now you have a model that was developed for robots, but that can also describe human behavior. This is very much the whole spirit of the course. For the robots, in practice, what we call the subsymbolic approach was the more powerful one. Here, when you really have to know what is target, what is obstacle, and track these individual contributions, you have to do some considerable work where you'd have to really track. Sorry, I'm pointing again at the wrong slide here. You'd have to really track these objects as objects to erect the correct force at every moment in time, which is actually not so easy, even though it can be done. While it's much simpler to just assume that you have a few sensors and that every sensor makes a little contribution like that, erects a forcelet. And that's what we then discussed under the subsymbolic approach. And that works perfectly fine, as I demonstrated in videos and papers and so on. And the one puzzle about it is, why would it work? Because if you do that, these sensors rotate with the heading direction. So if you think of them as contributions to the dynamic system, they are actually not contributions that are invariant. That would be really having here the correct form for every heading direction. If I'm looking at the heading direction, that particular contribution would be shifted and would so it would not actually describe the turning rate as a function of heading. And you see that here, where we're looking at the same obstacle, the same vehicle, but it's at different angles. It's pointing here or pointing there. And now, each of these sensors gets different sensor information, has different amplitude, and therefore these individual curves are really showing up in different places and are different, right? Here you, like from the sense of psi 5, you have a contribution, but here you don't have one of those and you have other contributions on. So the individual contributions are actually not invariant as you are looking at different headings. But if you sum them, the black solid line, you see that is approximately invariant under this rotation. So that really correctly describes the turning rate as a function of your heading for just any heading. And that is really why that works. And so it only works approximately because it's not a perfect invariance, but it works right. And that's one of the criteria. When you build an approach like that, you have to make sure that you're modeling the individual forcelets so that this property is retained. And we did some serious work in the past to try to establish that. I briefly took you into more advanced territory where I showed how you could do this one level higher in terms of derivative, that is, make the dynamical variable a turning rate, omega. And now you're actually switching from attractor to repeller and so on as you're turning on the fly. And I'm not going to ask you details about that because it's a bit mathematically complicated, and I just wanted to put that into the summary to remind you of that. However, I will be interested in comparing to the potential field approach. This was the most prominent approach when I reviewed other approaches to path planning. I didn't review the symbolic path planning through sampling and probabilistic and so on, because those are very evolved. I just really focused on the potential field approach. And I also did the dynamical window approach, which I think I skip here in the summary, because those are close to the attractor dynamics approach. In fact, the potential field approach is very close to it. It has this notion of a potential, which is also a dynamical system description. It's like using integrating the equation. You're saying you're going downhill. If you take the derivative of the potential, then you write a dynamical system where the rate of change is really just the derivative, the gradient of that thing. And you're building that up by having a target component that has a minimum at the target, obstacle components that has maxima at the obstacles, and then when you sum them, you express these two constraints. And when I say at the target and at the obstacle, I mean at the position of the target and the position of the obstacle. So it's in position space, not in velocity space, right? That's the major difference. So in the potential field approach, you're going in a transient. Behavior is generated by the transient. Some initial condition, you're going to the target, maybe here, going to the target. And as you're going to the target, you're being repelled from these obstacle locations. Your path is deformed by that. But it's the transient solution. So you have to make sure that all the transient solutions end up in the target and avoid the obstacles. And that's really different from the attractor dynamics approach, where you're only designing the attractor states, right? And you're making sure that as you move around, you're always hitting the attractor, and you have to make sure that that's, everything is slow enough for that to be the case. And you only have to guarantee that the attractor solutions are not violating the constraints, which is not always guaranteed. It's a heuristic approach that doesn't always work. The potential field approach is also a heuristic approach. It does not always succeed. There are cases where it runs into local minima, where it cannot escape, and it can be pushed against obstacles under certain conditions. And this group that did the human modeling actually made some comparisons where they characterized this problem of the potential field approach here by having a local minima with all these obstacles. You end up in a little, spurious attractor, like a mountain lake here in the downhill valley gradient descent. But the attractor dynamics approach can also have difficulties. This would be a correct solution, but here would be a solution that violates constraints when you go between these two obstacles. And that's essentially because these two push to the left and these push to the right, and these two influences can cancel. And that's also something that the attractor dynamics approach has to find solutions for. And our solution, as you might remember, was to design this so that in the maximum only two obstacles matter, like only these two here matter. And then you can make sure that the bifurcation happens. So the influence of other obstacles that are further away is dampened down, so you don't get this summation effect. I just see there's a typo here. Good. And here is sort of in a summary, that's maybe an important point to remember, because you did a whole exercise on that, and this was an exercise that those who did it had struggled with. And it's always interesting for me to see that difficulty. And so really understand that the two approaches are very similar in language, but because they are based at different levels of derivative, they are fundamentally different. In the potential field approach, you have position-like variables. The attractor is the target position, so the end position. you repel from the position of the obstacle, and the motion plan is the transient from the initial condition to the target. While in the attractor dynamics, the variables are velocity-like. The attractor is the direction to the target, the repulsion is from the direction to the target, and the motion plan is essentially at every moment in time sitting in an attractor, and that attractor may evolve, shift as the vehicle moves, right? So that's in a nutshell the difference. That's an important point. Because potential field is very visible, and you might have to always navigate that. Then I had this whole section on mapping and SLAM and orientation. That's what, when people talk about navigation, they actually often mean that knowing where you are and knowing where you want to go, not just planning how to go. Right? You're in the Navy and you're not even interested in obstacles. You're just going always to the next target. And so maps are essentially are based on making a mapping in the mathematical sense from the world to the map. That's a one-to-one reversible mapping, just like a map that you build concretely can be related to the world. That one location in the map corresponds to one location in the world, one-to-one. And you're all familiar with maps, right? You use maps in no longer. Everyone has Google or I don't know what's it called, Google Maps, I guess. Yes, it's also a map. It's a special map that is actually moving. The visual display is moving with where you are, and it actually solves the problem by using satellite navigation to tell you where you are on the map. That's why it's so easy to use your Google Map on the iPhone, because it always tells you where you are. And if you're lucky, it also tells you in which direction you're looking. There are really three things. You need to know where you are in 2D on the map, and you need to know where you're heading. Three variables, right? And generally, you need to know that. So in the more classical paper map, that's your first task, to orient, which means to find out where you're on the map and which direction you're heading. So holding the map correctly. You can do that based on landmarks and some kind of spatial reasoning. That's an important thing to know. There is ample work that shows that humans use map and animals use maps. For animals, it's actually less obvious how to establish that. And ultimately, the proof of the pudding is that animals can make shortcuts. That is, they have learned an environment and then they can find a new path they never experienced that they infer from the configuration. And in some circumstances, they can do that. That's sort of a hint that they have something like a map. And we didn't really go into detail into that. I'm just telling you that. So one important way of knowing where you're on the map is just if you knew initially where you're on the map, you extrapolate where you're going to be on the map after you made some moves. That's called dead reckoning or path integration. The equivalent word dead reckoning comes from the Navy or from navigation, ship navigation, and path integration is, I think, the more technical term. And so it's really the idea that you know your velocity. You have to know your velocity vector on robots. Typically, you have that from your control system, so you know your heading direction and your speed. Your heading direction, you might know, is actually a problem. You might know your heading direction if you have a compass, which is the case for ships with that compass or inertial guidance systems. In our robots, we actually don't have that, and you determine your heading by integrating your rate of change, your angular speed, and integrating that to get an estimate of your current heading, which is already subject to the uncertainty that accumulates, the errors that accumulate. And in the literature for SLAM, there are actually interesting algorithms that try to get an estimate of your heading from like visual flow, from seeing if you have any rotation in your visual flow, and that would give you some sensory information about where you're heading that's independent of your motor command. Because you might, your motor command, you might have slip, your wheels might not be precisely rolling, and there could be an error in your prediction of how you're turning. So when you have that, you can extrapolate to both get your heading direction and your position by integrating. And if you're just adding up, of course, then any error you make at any individual moment in estimating speed, heading, and so on, or even time, are just summed up. There's no way to reset them because you need ground truth to do that. And this need to periodically reset sets up the whole problem of SLAM that we'll get to, or using a map. And there's ample evidence that humans and animals do that. Some animals do it much better than humans. I might have mentioned this example of the desert ant. That's the most famous case because it's a animal that can only stay outside for very brief moments in time. It would be burned by the sun, dry up, and die if it stays too long. So it has to find its little hole where it hides, and that has a very, very good dead reckoning system to find that hole. Humans are not so great, and I showed you some examples of that. And robots all use some form of that. And then the resetting is typically done by having some map. So, for instance, having landmark information so that you know, oh, now I'm in front of that church now I know where I am and even how I'm oriented. And even though you're maybe not exactly in the spot you predicted, but you found close enough to the church to reset, and now you can start afresh in your dead reckoning from that corrected location. Right? That will be the principle of how you use landmarks intermittently. And for that, of course, you must have experienced that landmark before and therefore associated some kind of location with it on the map. If it's an external map that you have, then you just take the entry into that external map as your new starting direction. You reset your position estimate based on that and also for your orientation estimate. And there's a lot of evidence, study on what kind of landmarks humans use and animals use and so on. Generally, you want to use information that is not very proximal. So this idea that the landmark is an object where you are is actually not a good one because doesn't give you a lot of generalization. It's actually more typically you think of a landmark as something that you are seeing and you're not right at that location. For instance, say the church, right? You're in front of the church. And actually, the further away that landmark, the more invariant it is. And you can estimate, you can detect that you are in front of that landmark, even if your position varies a little bit. So you have a whole range where you can recognize that you're there. And there's direct support for this notion in animal research, where you find that animals search in a larger area if the landmark information is further away. So they are really looking at the equivalent visual angle as the one that controls how widely they are exploring spatially. I took you through this Axel Steinhagen model that makes that very operational, but I was going to ask specific things about that. That's too complicated. It's more these conceptual level that I might ask about. So SLAM is the notion to do these two things at the same time. That is, make a map and use a map, right? That's the notion, to make the map yourself autonomously as you are moving around and be able to use the map. And so one thing is that you do need this path integration all the time because you need to get you some position out of somewhere. And in SLAM, the way path integration is done is also optimized and is part of it. So where you, for instance, use sensory information to estimate your velocity. You have a velocity estimate so you can do better navigation. And what you do is then you have some algorithm for determining when you are going to take the sensory information and put that down as landmark information. Typically do that at some discrete points. You have some algorithms for doing that. There are different ways to do it. You, for instance, based on there having been significant change in the sensory information, or you just do it randomly in some sampling sense. There are different ways of doing it. And at those points, you store the sensory information that you have. That could be like a depth profile you get from your laser rangefinder, or some sonar information and other kinds of things. You put that down in your map as information. You have it actually in a database, and you associate it with a position in the map, which is the position that you estimated from your dead reckoning, that at that point, that's where you were. So when you have these points, and these points hint to information that is stored, these would be the estimates where you thought you were when you acquired that information. And then the famous loop closure problem is that if you approach a point again after some action at which you stored that landmark information, that you recognize that it's the same, and therefore now you reset your location in some way to say, aha, this is now where I've been before, and if I still make entries into the map, I have to correct my last entries so that they're consistent with that previous estimate. And that's where there is some SLAM algorithms have some sophisticated algorithms how to do that. I mentioned the rat SLAM that's based on hippocampus analogies. I didn't put this here into the summary because, again, felt that was too far afield. And that's a approach that actually doesn't do anything special about the loop closure. It just keeps doing the same thing. That's actually the biological solution, that you just overwrite the map information every moment in time. It doesn't store, in the same sense, very deep sense information. It really just stores something much lower level. But I'm not going to go into that more. So that's all the vehicle stuff. So we talked about 40 minutes or so about the vehicle part of the course, and I made in the course this whole distinction that vehicles are different from arms, right? We'll come to arms next. And they are different in that in the vehicles, the sensors move with the vehicle, right? That's how the whole mapping problem arises, because you have a new reference frame. Not everything is visible all the time. If you have an arm, it's mounted on a table, it has some sensors, and it will be always, it's locked in location, right? It doesn't have to estimate where it is. And it might have sensors to tell it where it is. You look at your arm, you know where the arm is, because the camera is fixed in, actually this camera is active, can move. You have some estimation problem of where it's looking, but at least translationally, it knows where it is. And so that's a fundamental difference, that when the sensors move with the action, then you're in one case, it makes a lot of things easier because you get very simple algorithms to navigate. I mentioned a few of those. While here you have more abstract transformations. You have to sort of estimate where this arm is based on a sensor that doesn't move with the arm, and therefore you have to really know the length of the arm and what it would look like from different positions and so on. But on the other hand, it's also more powerful, because once you have that, you can actually direct your action at objects in the world, while the other has this very limited just target acquisition and obstacle avoidance kind of approach. It doesn't have more detailed things like grasping and manipulating and so on. So we call these things also manipulators, these robot arms, because that's the goal, to have to do things on objects, not just move to the objects, but do something with them, grasp them, manipulate them, transport them somewhere else, and so on. And that's where robots are still struggling to do a lot of those things. So I gave you 3 lectures about robot arms that were really classical. That is, industry robots face the same mathematical issues. In classical textbooks, you have these treatments. So this is the forward kinematics, it's the dynamics and the control. And sorry, the timing and the control. And I'll just take you briefly through that. It's, of course, lends itself also to easy questions because it's very classical. So here I have a summary of the forward and inverse kinematics, and I have more detailed slides about that in a second. So in the robot arms, you always have 2 levels of description. One is the degrees of freedom of the robot arm. Every joint angle is a degree of freedom, and I'll come back to that in a moment when we talk about dynamics, that there are the joints restrict the degrees of freedom. Degree of freedom is how many things you can freely vary, the initial conditions that you can vary, right? And the individual segments are rigid bodies, which can be shifted in 3D, can be rotated in 3D, so they have 6 degrees of freedom. But when they're mounted in a robot, they have typically only 1 degree of freedom, because they have a revolute joint with the previous segment, and then they can only rotate around one axis where the revolute joint turns them, like this one here, around one axis. And so they have only 1 degree of freedom, right? So per joint, you get 1 variable that you can control. And so that description of these variables you can control, that's the joint configuration, the vector theta, while the things we're interested in are typically positions of tool points. This is like the hand. It's sometimes called the end effector. Could be the tip of a welder, or the tip and orientation of a spray can, and so on, depending on what you do with a robot. In classical robots, it's arranged that the number of degrees of freedom hidden in these variables are the same as the joint angles. So when you have a rigid body that you want to freely configure, like the position and orientation, you have six variables to control, like three translations and three orientations. And in that case, uh, typically you have six joints, so that choosing there's a one-to-one mapping between the six joints and the six configuration degrees of freedom at the task level. And it's in this setting that these kinematics here are formulated. So forward kinematics would be predicting where your hand is from your current joint vector. Inverse kinematics would be predicting what kind of joint configuration you need to get your hand into a particular position. And it's that inverse kinematics that you need, because typically your task is about bringing the hand in some location. So you have some desired value for that. And then you need to know what is the desired joint configuration, right? Both have a differential form. So taking the derivative in time, you get that the hand orientation and position rate of change is a function of the joint velocity that has a matrix here in front that's called the Jacobian that only depends on the configuration. And that can be inverted under some circumstances by just inverting this matrix here. And that's the very convenient thing, that it's linear in the velocity variables that you choose here. And therefore, you only need to invert that matrix. And that's very easy. While inverting this nonlinear function with the sine and cosine functions here, computing f to the minus 1 is much harder than computing the inverse of a matrix. So the differential form is very often used in practice. So concretely, these kinematics themselves look, have the sinus and cosinus functions. I'll point to some complication that leads to when you invert it, you have to solve that exactly. That involves solving sinus, cosine, arcsine, and so on functions. That's where a problem arises. This is the problem of the leaves. That is, there are often more than one solution for the inverse, and I'm talking about non-redundant arms. That is, arms that have the same number of joints as the degrees of freedom of the hand, but they still have these solutions here because they don't have the joint limits we humans have, and therefore they can reach this way and that way. If this is your elbow, your elbow is limited. It cannot change sign. It cannot move beyond a joint limit. So you can only realize one of these two leaves. But industry robots typically can do that, and it's a feature because you can have much more reach space this way. The human arm is more limited in what places it can actually handle objects in. And that's a complication of using inverse kinematics. We didn't go deeply into that. The other problem in inverse kinematics is the singularities, that there are points when this inverse fails to exist or becomes very unstable. So it becomes very sensitive, and that's typically at the joint limits. If you go stretch your arm out, like stretch it here this way, or you can also stretch it by rotating inside, then you reach positions where in one direction space you can no longer actually move, and it will make the end effector position become a sensitive function of some joint variables. It's really in the orthogonal direction you have this sensitivity, and that's just to know that that's a problem. We stay away from. Humans do have things like that, like at the limit of their joint angles. For instance, upright stance is like that, and then you have to have some strategies to how to avoid moving through those places. We didn't go very deep into that. Redundant kinematics is when the actual number of degrees of freedom is really different. Typically, you have more joints than you need. If you have fewer, then it's sometimes called underactuated. I didn't go into that. So here would be an intuitive human example where you would have three joints and you just want to control positions, the 2D position of your end effector position, just to make it easy. And therefore, it's not invertible by definition because you have more thetas than x. So you have too few equations to determine the thetas if you have a desired x. And you can find solutions, it's called pseudo-inverse here, by arbitrarily selecting one of the possible solutions. And these pseudo-inverses select them by having different functions that they optimize. Sorry, I'm again pointing at the wrong screen. So this would be the pseudo-inverse, and they minimize some, for instance, this minimizes joint velocities. That's the Penrose. What's the other guy's name? I forgot. More Penrose, I think. Pseudo inversion. There are other pseudo inversions that minimize energy or other things. Uh, so those are routinely used for non-redundant for redundant robot arms. There's a whole literature about that. I hinted that human arms are redundant, and and that has some interesting implications, which I hinted at, but I wasn't going to ask you much about that. So a lot of my human motor control work is about that problem. It's sometimes called the synergy problem. Yeah, good. Yeah, and then we had timing, so the generation of time courses of that make a movement, right? You make a movement. It's not just computing your desired positions. It's generally the whole time course. And in the robotic example, the vehicle example, we didn't talk about that. We just said, well, you have to give it some velocity. We even didn't think about the path velocity, how fast you move along the path very much, even though one can do that. That's because there we're not really imposing timing constraints. That is, we're not saying we want the vehicle to arrive at a certain time. It just moves ahead and it takes as long as it takes. If it goes around obstacles, it takes longer than if it doesn't have to go around it. And that's actually the state of the art in the vehicles. You don't really control the arrival time. Even if you're a human and running to catch a ball, you do have to do that, right? You have to be at the location where the ball is falling in time. And so that's different. There you can't just take as long as it takes with your velocity choices. And so this problem of timing is important for autonomous robots, and not so much for conventional robots, where it's just a question of how you parameterize your curves. So they are more like vehicles. And I point out that in conventional robots, you just use some arbitrary functions of time, often polynomials. There's some other approaches so that you can, through these parameters, determine when you are going to be where. You can design the velocity profile to be a nice one that you can control well, and so on. So this is done in programming mode. There's nothing that is really considered to be very intellectually challenging. While in autonomous robots, it's not feasible usually because you're trying to go to a place that you only know about through sensory information. And as you're going to that place, I'm also saying reaching, right? Going to an object, the estimate of where that object is might change, or it might be moving, for instance, if it's a dynamical environment. And therefore, you have to update that time plan at every moment in time. Now you have to really worry how to do that, how to do this updating. And that's where people take inspiration from how humans do timing, because human movement is timed. Pretty much all human movement is timed. When you're locomoting, you're making sure that your left and right limb are alternating, and within the limb, you're making sure that the knee and the ankle really have the right relationship. If that was going to drift apart, you would be stumbling and doing a very bad job. And speaking, this very fine articulation, coordination of the articulators, where you make sure that your lips meet exactly when you make a B, and your tongue, comes to the right place at the right time. When you chew, right, you have to move around the objects in your mouth and make sure that at the right time you retreat so you don't bite your tongue and so on. And then, of course, making music is the most famous example of where it's important when you hit the note, right? It's not just whenever you arrive, right? It has to be at the right time. So it's true for these rhythmic skills, but also for discrete skills. When you reach and grasp, for instance, you're really making sure that you open your hand in time and close your hand just in time to grasp. When you catch, that's particularly clear that that's important. Where you close your hand too late, the ball is going to bump off. If you close it too early, you're not catching. And you also have to be at the right location where the ball is coming, let's say, at the right time. That's something that's deep in our nervous system. We are hunters, and our interaction with prey is about catching, essentially different forms of catching, and we're very good with that. There are subtle gender differences, for instance, in that skill that are not related to physical force, that reflect that men used to do more hunting than women in evolution. And that reflects that it's a difficult thing, that there's a fine tuning in our brain for things like that. And a lot of infrastructure is spent on that. It's a bit more, the cerebellum, that's a Kleinhirn in German. It's a major structure that is involved in doing that. It's still a bit of a mystery exactly how it does that. And we humans are the most skilled people. I mean, when you look at pianists, it's the most impressive perhaps. Can they coordinate all their fingers to do all these time intervals and so on? And when you handle an object, you can do this. Even I'm not very skilled, but you can do this in a way that makes sure it doesn't fall down. So you always anticipate that now you have to give it new support and so on. So that's very, very, very skillful. So coordination is really this maintenance of desired timing relationships, and desired again translates into stable, that is resisting change, compensating for change, components of movement. And that has two different senses that I briefly pointed out. One is relative timing, which is the more important one. The absolute, there's absolute timing. So I illustrate here through this artificial curve that two somewhat irregular looking time series can be very well coordinated in the sense that the same events are lined up. Like here, this zero piercing event is very closely lined up in one curve and the other. So the time difference is small as a percentage of the periodic time. So it has relatively precise relative timing, even though the absolute timing, if you look at the intervals where the piercing occurs in one, that varies a lot. But they're both coordinated, right? And that's a very typical thing that we observe in animal and human motion. So, for instance, if you look at an animal locomoting on rough terrain, then the relationship between the different footfalls remains quite stable, while it might go slow or fast depending on how big the gap is or exactly what the terrain is like. And the account of how animals and humans do that is that they generate the time courses from also an attractor dynamics. It's sometimes called an neural oscillator. It's in the brain, it's a neural oscillator. If you model it, you can make any kind of oscillator. An oscillator that has these stability properties is called a limit cycle oscillator, stable limit cycle. That is, it's a periodic solution rather than a fixed point solution, and it has the stability property that is from neighboring solutions you're attracted to that oscillator solutions. That is actually the mathematical theory of clocks. So if you look at classical clocks, with the escapement, grandfather clock, or even electronic clocks and so on, mathematically speaking, there are stable limit cycle oscillators. So that's why you can start up a clock and it gets back to the rhythm. If you perturb it, it will get back to the rhythm by virtue of that property. And I briefly gave you an exercise where I showed you that the generic neural dynamics of excitatory inhibitory populations make these oscillators. So this is something that those of you who did my winter semester course, and it's only maybe one or two, will then see that it directly feeds into that. It's sort of just an extension of that. And that's the whole theory. There's a big part of this now in deep learning. The generalization of this kind of idea is called liquid state machines. And liquid state machines are just very large ensembles of neurons that are randomly parameterized and can generate all kinds of time courses. And from these, you can mix together any desired time course by a learning algorithm. And this is now also used in transformer networks and other things like that, with sometimes under the label of liquid AI and a lot of other wrinkles in there. So this was like the most trivial version of that. So in this course, it was a bit isolated. I'm not going to ask you any detail about this here. So whatever the mathematical formulation, coordination comes from coupling such oscillators. So if you have more than one oscillator for the different components of movement, for instance, you can couple them, which really just means that in one equation for one oscillator, the other one, number two, shows up, and vice versa, some state variable shows up. And that tends to generate that the oscillators come into a fixed timing relationship. Very typically, if everything's symmetrical, it will be that they are synchronous, and two clocks, when you physically couple them, will synchronize. Huygens observed that centuries ago, that even just hanging two clocks onto a wall and through that wall they are coupled slightly, they will tend to synchronize. And there's some cool videos online where you see that. For instance, clocks mounted on a little cart, and just the inertia of the of the swinging pendula will make that after some time they are synchronous. You need some friction for that to go. If you can choose coupling so that it's not synchronous, so it's one is leading and the other is delayed, and there's a whole again a whole literature on that. So that's the core idea. And so that means that you have a way of creating stable timing relationships that are not based on computing exactly arrival times and departure times and then updating them when you get the information. It's just continuously running. And by this coupling, make sure that the two stay aligned. And that's really what's used in a lot of these autonomous robots that, for instance, the ones that the locomoting machines, I mentioned this Kodichek notion of template anchor system. So there's sometimes a way that you describe at a more macroscopic level the timer, like one of these legs of these hopping machines or these like these Boston Dynamics robots has an oscillator running, and that oscillator is translated down into the control of all the limbs and so on. But the level at which the coordination takes place is at the level of that oscillator. And then it gets signals from the other oscillators, and that may accelerate or decelerate the limb oscillator that you're looking at so that it stays in sync with another limb that maybe was delayed or advanced because it hit terrain, let's say, was advanced because the terrain was closer and hit ground earlier. And now the other limb has to also start its cycle earlier so that they stay in alternation. And the details of that are complicated, but that's the basic notion. So that was the second chapter. That's classically just a very simple parameterization. In autonomous robotics really becomes quite different. While the kinematics is sort of the same in autonomous versus classical. And then control, that's the next. Did I only show you the wrong slide the whole time? I don't know. So I always get confused about these two screens here. So this is, I'm not sure I showed you the right screen here. Good. So just complain if I don't do it right. Sorry. So the last is this kinetics or control. And um, and here this is about the dynamics of arms, right? The physical dynamics. Physical bodies have inertia. They will accelerate under gravity, and then you can insert forces at the torque by motors at the joint angles. And control has to do with this physical dynamics, how to deal with the forces, how to generate the forces and angular momenta or the torques, and then predicting what will happen and seeing how to get them into the right coordinates. And the problem for robots is that there is this big difference between their degrees of freedom as rigid bodies, or when they're free, and when they're mounted in a chain. They have constraints, right? So when they are rigid bodies in the 3D world, as I mentioned before, they have 6 degrees of freedom, translational, rotational. We know Newton's law, inertial law, so we can write down the equation of motion in terms of Newton's law. And then we get a lot of equations. But when we mount them in a chain with revolute joints, all these degrees of freedom are now constrained. So we have constraint equations that would eliminate almost all degrees of freedom. From 6 for every joint, you can eliminate all but 1. And it's a question, how do you do that in the equations? The Newtonian equations of motion. That becomes very complex. It's been done in some very older work, but it's not actually the current state of the art. State of the art is to go to the Lagrange formulation of dynamics. That's not a new thing. It's 19th century. That was developed a long time ago, and it has been the framework that's most successful in robotics. There are really 3 frameworks for classical mechanics. Just the physicists will know that. Is the Newtonian framework that's used based on this law of inertia, that without forces you have constant velocity. And then the Lagrangian framework I'll explain, and the Hamiltonian framework that lends itself to generalization quantum mechanics. That's why it's very famous for that. But it's not so good for problems with constraints. So Lagrange is just right for mechanics with constraints, and that's what robot arms kinematic chains are. They're constraining rigid bodies to move in subspaces. So when you add constraints, what you do is you just introduce what are called generalized coordinates that is just some numbers that characterize the kinematic state of your mechanical system. So here, for instance, the two joint angles, theta 1, theta 2, uniquely characterize the state of this two joint arm. And you can write down then the equation of motion just in terms of these variables. And that's the Lagrange equation. In the lecture, I even kind of derived that from the principle of least action, but I'm not going to ask you that. That's just a very, very brief tour through something that in the introduction to theoretical physics and mechanics is like half a semester. So I don't want to force you to do that. But the shape of the equations that are the result of this kind of thought is something that you should recognize. And that's the typical shape of these Lagrangian equations for open chain manipulators, where theta are the joint angles. So you have an acceleration term, you have a velocity term, and you have a term, sorry, this almost always doesn't show up. It's just a position term. And the acceleration term has in front of it a matrix. That's the inertial matrix. So inertia is like mass in rotation, right? If you have a very heavy mass on a long stick that has a lot of inertia, so you need to generate a lot of torque to get it to oscillate, to accelerate. And if you pull it in, then you need less of that. So that's the inertial moment here. We have to model that, and that is something like mass in front of the angular acceleration. These are these apparent forces. The fact that you're rotating makes that it's not an inertial frame, right? Even if you have a constant rotation around a joint, then everything that's downstream from that joint is in a rotating frame, and there's a rotating frame's acceleration toward the center of rotation, right? So you're opposing the centrifugal forces. These are the forces that do that are called centripetal forces. In German, Zentrifugalkraft. And that's an apparent force that just comes from the fact that it's not an inertial frame. And the more sophisticated one is the Coriolis force, which shows up, is also an apparent force that comes from looking at an object that moves on a rotating platform. There are very beautiful videos now on YouTube that illustrate these ideas. If you worry about those ideas, just look that up. That really make that very clear. And so they are depending on the velocity, and you don't need to know the terms, right? But you need to understand that these terms, these two terms do create what is called interaction torques. And interaction torques make that if you are accelerating one joint, it affects other joints. So at the inertial level, it's very clear. If you accelerate your elbow, then there will be the wrist will be in an accelerated frame, and that will make that there are forces acting on the wrist. You see that if you accelerate your elbow, your wrist would flap around from that. So there's some force transmitted from the torque at the elbow onto that. As a human, you would stiffen up and compensate for that. And in a robot, you have to deal with that. And the classical way is just to control it away, to discover that the interaction torques create some disturbance for other joints, and then you have a controller to make sure that that disturbance is counteracted. That is somewhat of a problem, because then the control action also perturbs other joints and sort of chains down the whole thing. And that's why robots have to be relatively strong to control against that. And the more sophisticated approaches try to anticipate that and already insert the correction before it is experienced. And these are called sometimes torque, modeled torque control. And here I don't go much into that. The gravitational term is more trivial, right? If you change your configuration to gravity, there are different angular momenta created by different torques essentially generated by the gravitational angle on your joint, and that can be treated trivially. The generalization is, the Lagrange formulation is really for conservative systems without any change in energy. But if you insert energy, it becomes an open system. You have an engine, motor there that burns energy, and you can model that by figuring out at which level this enters. So if you have that formulation, then these would be what is conventionally called a joint torque. There's a vector that for every joint that is showing up here, you have a torque vector, and that's what your electrical motor does. So that's just the mechanics per se, and now the control consists of inserting the right torques to achieve the right thing. Yeah? And This means inserting the torques as functions of time that you want to do to get the right movement. You have to have a model to do that. And then the control problem is to possibly adjust the torque that you send there as you're sensing that your arm isn't doing exactly the right thing, which could be due to the fact that you made a mistake in computing this torque, or that you're not estimating this right. There's some parameters that are not right, or there's some physical interaction with the world that changes the equation in ways you don't know. And that's what you have to react to. And so the control scheme, the general notion is that you have a desired uh, time course of something here of your variables, and that would be your plan. The timing and plan would generate that time course, and then the controller makes sure that your state variables, the thing that you want to move, does the right thing. And you observe what your arm does, and the controller can take into account both the desired and the observed state and get from that some information about the discrepancy, how much you're deviating, and will send down a signal that minimizes that deviation. Now, in the robot arm, there are two levels of control. There is this inner and the outer level of control. The inner level of control translates essentially electrical signals from the amplifiers to the electrical motors, the torque motors in there. And those together with transmissions will generate the physical force and torques. And there's some feedback that makes sure that you are sending the electrical signal down that generates a desired torque or force. And that can be done very well these days with certain kinds of motors. And so that robotic planners are not really dealing with that. They're just buying the motor from a servo motor from a company that has figured that out, has a good control system in there. And so the control that the roboticist needs to worry about is only, I have a desired joint acceleration, joint velocity, or whatever it is, and I need to get the torques out of this device that do that. And so that is something that's given to you. And then you're controlling, you're looking if the motions really correspond to what you wanted, and then controlling the desired trajectory that you put in, the control signal you put in there. So the classical control of a single joint, just a PID controller. So your desired trajectory is transmitted to the transform through some gain value into the desired torque, and it's your motor description that tells you how much voltage you need to get which torque. And if that's your only signal, that would be pure feed forward. That is, you're just saying, this is the torque I need to get that desired trajectory. But in PID control, what you do is you observe the joint angle that you actually achieve, compare it to the desired joint angle, and transmit only the error, the deviation of the joint from the required joint. And the proportional term would just say if it's too much, I send something that opposes that. If it's too little, I send something that amplifies that. Your differential would do the same on the rate of change. So if I'm moving too fast, I'm sending something that slows. If I'm moving too slow, I send something that accelerates. And the integral term is the tricky one that says that if I have so far moved too little, I'll add something to move more. And if I've so far moved too much, I will subtract something to move less. So far, meaning integrating from the start of the movement. And these three together will, under many circumstances, achieve the movement goal. The integral term, as I mentioned, is sort of the tricky term. It can deal with systematic errors, like a gravitational contribution that prevents you from reaching the goal without some constant torque that you constantly have to insert. And that's where it's good. But if the discrepancy comes from an error in estimation, like that your target is inside the table, so you didn't quite get the target to be at the right location, then the robot will build up more and more force to get to that target inside the table until it breaks the table or it runs out of power. And so that's the term that sometimes causes trouble. And a lot of control in conventional robot arms is just the same for all the joints. It does the same thing along the entire kinematic chain. Then the joints are controlled independently. And that means that the interaction torques are disturbances for the different joints, and they are being suppressed by PID control. And that is how a lot of robot arms still work, and that works very well. And the computer torque controllers, where you compensate for these forces, they're also now common. They were not common for a long time because of computation constraints. They make it a little bit milder. That is, you are not experiencing fully the interaction torques as perturbations or disturbances. You're already sending something that anticipates that these interaction torques will arise. But I'm not going to go into that in the exam. Yeah, so finally you had these lectures by Lei Zhang, and I wasn't going to ask any of the neural details of that. Maybe the one core idea to understand is that that muscles are springs. They are spring-like. So when you change the joint angle, the force that a muscle exerts on the joint it's not a linear function, but it's a monotonic function of that extension. So for instance, if your agonist here, let's say that flexes the muscle that resists a movement, the antagonist, sorry, that would create more and more force if you extend it from its desired length. This would be its desired length of the muscle that translates into its desired joint angle. And the agonist, conversely, if you're, the muscles only pull in one direction. So the antagonist cannot push in that direction. So it would only generate force that's in the opposite direction, and that its equilibrium point would be here, where it would no longer make any force. And if you're getting to a shorter joint angle, it will be extending the joint. And the red curve would be the sum of the two, and that would be like a single spring. It's a nonlinear spring, and that would mean you have a elbow angle at which these two compensate exactly, and the net force would be zero. And if you're extending it, it would resist that extension, trying to get back to this. If you make it narrow, it would the other direction, it would resist that and want to go to this default value. So this is sometimes called a equilibrium point of that joint angle. And it's sort of like an attractor dynamics kind of thing, right? It's mathematically speaking, you need damping to make an attractor. But it is like an analogous idea that is you set an attractor at the joint configuration you want, and then the muscle periphery will automatically go to that attractor. That's roughly the idea of that kind of approach. By having these two opposing muscles, you can make sure that they both make some force. Like, at this equilibrium position, the net torque is zero, but there's a force from the agonist and from the antagonist. So they pull in opposite direction. And that gives your joint a certain stiffness. In fact, the slope here is determined by that, this co-contraction. Both muscles are active. When you show your biceps, you're doing that, right? You're activating your biceps and triceps, opposing muscles, and they make force on the joint, which has zero torque because they cancel, but they resist change, so they make it stiff. And that is something that is being actually used to control stiffness in human movement. So there are efforts. So in the nervous system, this is based on reflexes. I think Li Zhang told you a lot about that. So these are reflex, meaning that if you have a muscle, there's a sensory organ in the muscle that senses how long the muscle is. And if it's stretched, it sends a signal to resist stretching, so to contract the muscle to shorten again. That's the stretch reflex. That's the most basic reflex. And with that reflex alone, you get that kind of behavior already. And there are more complicated reflexes than that. I should say that there is a huge effort in robotic research to emulate things like that, to make spring-like actuators. And some people are really literally using springs. They have an electrical motor. The spring is sort of has a long cable, and you can sort of wire it up and stretch the spring to different amounts by shortening that cable. And this is like having a motor, but also a spring in series, and that gives the joint a little bit of a spring-like property. If the spring is very stiff, it's just used to measure torque, and there are some torque-controlled motors that way. But if the spring is relatively soft, then it emulates human movement, which avoids using this very large amount of force, which is dangerous, can break things. So if you don't understand exactly how don't exactly know where the surface is. For instance, you're just choosing a point inside the surface as your target point, and then as the robot arm hits the surface, it presses against the surface just with that spring constant. And if you make it not too stiff, that table will support that and you will grasp that table. In fact, you can do grasping that way. You just plan a configuration of your fingers inside the object, and that will mean that the springs, the equilibrium position is inside the object. And as the object resists, the springs press against the object, but they only press with that force that the spring, depending on how stiff it is, the spring exerts, and that can be just right to grasp it, but not enough to break it. And you control that. It's not. There's some deployed systems like, but this is work in progress. It's so difficult because when you do that, then the normal control doesn't work so well, right? The normal control would moving your arm around, and now you have these springs that are really sluggish, and now as you're trying to move the arm to a location, you have to say, does it overshoot? Does it oscillate? Does it actually even get there? It will get there with delay and all kinds of problems. So to reconcile targeted movement with this property of being compliant, that's sort of the challenge here. Yeah, so that was a very short take through the course. It's certainly been interdisciplinary. We've been going from muscles and human navigation and hippocampus to classical mechanics and control and motion planning and timing and so on. So it covers a lot of different things. The common thread, as you see, is dynamical systems. So we really made it clear in this planning with dynamical systems that we'd use the attractor dynamics, the stability, and all that. But similar concepts are used in control. And the dynamical systems for actual dynamics is not actually attractor dynamics, it's conservative dynamics, the Lagrangian equation, but it's also dynamics. And in SLAM, there is dynamics hidden. In fact, the biological version of SLAM uses the heading direction as the variable. So I hinted at that. And there's some neurodynamics in there. And the timing is also the dynamical system with coupling and so on. So the dynamical system view goes through all of this. I only made it concrete for this robot vehicle path planning because it's easy enough to do in a course like that. But in all the other systems, you have dynamical systems as well. So that's really, you could say that that's a core concept in robotics to understand every layer in terms of state variables in dynamical systems. Yeah, and you had some experience reading papers from different domains and writing mathematical technical material, even though we did not go very deep into the technical aspect of it. You didn't solve complicated equations, but the capacity to communicate about equations and dynamical systems, so on, by making plots, by describing variables, by using the right terms and so on. That's something that you experience in the exercises, and the exam will test that. It will ask you to describe with drawings and variable names and text the behavior or a solution to a robotic problem, or the behavior of a robot that is, has a certain dynamical law.